Oh, okay. All righty. Good afternoon, everyone. We're almost at the home stretch here. My name is Kevin Lee. I'm from New York University and also building diagnostic robotics. And today I'll be sharing with you some of our preliminary work in exploring self-supervised GPR representation learning for building rooftop diagnostics. Now, when I mention building rooftop diagnostics, I'll be specifically referring to moisture detection on building rooftops. Now, moisture detection, or rather moisture damage, is a significant concern for the commercial building industry as it contributes to a lot of structural damages to buildings as well as reducing their overall energy efficiency. And so if we had a robust and reliable detection system that can find these problems early and prevent them from escalating to bigger problems, of course, that would be very desirable. Our work here actually can be also considered an extension of a previous paper submitted actually last year to ISARC that first introduced the idea of applying deep learning methods to GPR data processing for the express purpose of rooftop moisture detection. And in that paper, they discuss using supervised techniques as well as using data from a hand-built custom test rig. Our paper here departs from that by first exploring self-supervision as a potential solution, but also we are using data collected from many actually real-world building rooftop data sets. So before we begin quickly, just for quick background on what exactly is GPR. GPR, or ground penetrating radar, is a non-destructive technology that uses electromagnetic waves to detect changes in the properties of the scanned medium. Now, the GPR sensor has an antenna that emits these EM wave pulses and another antenna that can record the reflections over time. And the key property for that influences the GPR readings is something called the dielectric permittivity. And we believe that this property will be key in allowing us to create some robust classifiers to detect moisture damage. In this paper, we'll be discussing GPR in the two main dimensions. The first being the A-scan, or otherwise known as the trace. The A-scan is a representation of the reflected amplitudes of the electromagnetic wave recorded over the time domain, measured in a two-way time in nanoseconds. And this can be considered our one-dimensional representation of GPR data. We'll also be discussing GPR in the form of B-scans, or radargram. And B-scans are simply a collection of sequentially scanned A-scans in a straight line. And as you can see there in the illustration, you can kind of get an idea of what they look like. And so now that we got some of the background out of the way, what exactly are some of the challenges we may come to expect when applying deep learning methods to GPR moisture detection at scale? And if you're interested, that's our robot in the bottom left corner. So when it comes to deep learning, one of the first things we typically consider is the data set, right? What exactly is it and how will we create it? Considering that we are trying out a task that's relatively new, right? Rooftop moisture detection. We don't exactly have a large or any publicly available data sets to rely on. And so if we want a robust classifier that can detect moisture on rooftops, we're going to have to create a manual data set. And this, of course, is very expensive, it's very labor intensive. There are synthetic, or rather there are GPR simulators like GPR Max that can be used to create synthetic scans. However, we are cautious of using simulators because there are a lot of inherent variability in the way building rooftops are constructed. There's different materials and compositions, and also different features that may lie underneath the surface. So it's hard to capture all that variability. Considering that we already had a lot of unlabeled GPR rooftop data collected using our robot in previous projects, we come to ask the question, well, what if we try self-supervision as a potential solution to our problems here? We also find that in literature, GPR is typically interpreted or rather the B-scans are interpreted as images. Considering that B-scans may span many meters in length, and we are particularly concerned with kind of the scale of A-scans, which are at the centimeter scale, we come to propose or suggest interpreting GPR as what we call a contextual neighborhood of GPR data, which is simply a sequence of A-scans instead of full images of a B-scan. And this allows us to explore different model architectures, like, for example, a transformer. So when we're using self-supervision, our goal is to analyze the learned latent space of the deep learning model after it learned or trained on certain pretext tasks, say reconstruction. And so reconstruction, if we were to ask a model to train on reconstructing GPR scans, the model should be able to encode that trace into its embedding space and then learn to deconstruct or reconstruct it based on the information that was encoded. And so if we want to evaluate the latent space of our deep learning models, some of the techniques we may use include dimensionality reduction techniques like TSNE or TSNE. We can also measure quantitative metrics using k-means clustering, for example. Now, we use clustering because it may be reasonable to expect that if the model is learning anything semantically meaningful in the latent space, that it should be organizing the latent space into in a certain way, maybe traces that are indicating the presence of moisture should be encoded near each other, but far from traces that are encoding maybe dry signals. And so to this end, we evaluate 4 different deep learning models. We use a basic autoencoder, a variational autoencoder, a transformer-based autoencoder, which will be using the sequence of A-scans idea, and a masked autoencoder, which will be using for our image-based method for comparison. And of course, we are also using a baseline that does not use any deep learning method. So how did we do? As you can see on this figure on the, yes, you're right. Every method was successful in reconstruction. And this scan was chosen specifically because you can see some of the features we may come to expect when looking at GPR scans on buildings. On the right-hand side of the scan, you can see something that looks like, okay, I got my directions messed up, sorry. You can see a hyperbola shape that may indicate something like a point object, like a pipe. On the other hand, other side, you see kind of like distorted parts of the scan that usually is indicative of the presence of moisture. In this case, it's most likely surface ponding on the roof. And so now that we see that every method was able to successfully reconstruct the scans, we can move on to analyzing the way it organized the latent spaces. And so here we have a figure that demonstrates all the, or illustrates all the learned latent spaces of each method. The figures are in 2D, but color is also provided to show separation in 3D space. And so we can see from the autoencoder, the VAE, and the TAE, which is the transformer-based autoencoder, there appears to be some sort of weak clustering happening, but it's not exactly clear. The interesting thing here is the masked autoencoder. We can see that there are a lot more strong, distinct clusters here. And so maybe if we take a look at a specific scan and see how that's encoded, we can get a better idea of what's going on. And so here, in this visualization, we can see, again, the same scan from a reconstruction. Now, I've taken that and passed it through the deep learning models, and we have an output that shows the way that scan is being encoded. Really quickly, the columns in the first 4 methods there are the A-scans, the traces, and their colors correspond to the color points in the 2D latent space. And the masked autoencoder is like VIT-based architecture, so it uses the 16 by 16 patches, image patches to encode. Now we can see that there's actually some interesting behavior here, particularly with the trace-based methods. We can see that like traces are kind of encoded near each other, as you can see from the colors. But the interesting thing here is the masked autoencoder, again, looks like there's no real pattern going on here. So that kind of hurts the idea that what we probably saw in the previous results, that the masked autoencoder is actually learning anything interesting here. So the results here are somewhat inconclusive. And the similar story can be seen in the clustering metrics here. The basic autoencoder actually scored the highest across all methods for overall the K clusters. But we see that the highest silhouette score here was under 0.4, which indicates a rather weak clustering performance. So again, it's not exactly clear if the models are learning anything semantically meaningful, yet it's still kind of somewhat interesting that we can see them in some of the behaviors in the way it's organizing the spaces. And so again, this is a kind of a preliminary look into exploring the way we can apply self-supervision. So this is ongoing work. We're still trying to figure out what may be the best methods to use to apply self-supervision, because we still maintain that there is a lot of benefits to be had from self-supervision, especially in the way of managing data sets and training a classifier. We attribute some of the difficulty or some of the poor results here due to maybe the variability in the building rooftops. They have a lot of different materials and features. So we'll be exploring different maybe pre-processing methods, maybe to reduce the noise in the GPR scans, but also maybe entirely different self-supervision paradigms, like maybe contrastive learning. And so this work is supported by an SF grant, and your contact details as me and my advisor, Professor Chen Feng.